field of quantum is very vast, and it's indeed very exciting what's happening over the past years, or even now more than a decade, I think. I'm mostly specialized in one, what we call one pillar of this quantum technology, which is quantum sensing, and mostly quantum sensing using atoms, cold atoms that we cool down at almost absolute zero. It's only like millions of a degree above the absolute zero. So the atoms do not behave as atoms anymore. They behave like waves, like the waves on the sea, on the nice sea outside here. And we can use these waves to actually measure very precisely quantities like gravity, acceleration. And I made myself one of the specialists in this inertial measurement of quantity of like using quantum sensors for this. The temperature I mentioned with atoms is the coldest temperature you can ever reach. I mean, it's much, much colder, for instance, that the temperature which is needed to make the quantum computer that everybody thinks about, quantum computer like IBM is building, for instance, where they use these big fridges with liquid helium in there to reach temperatures that are almost at absolute zero, but that are like thousands of times hotter than the atoms we're basically using for our sensors. There are many challenges for this technology to go forward. We are already quite far because everything did not only happen in the last 10 years. I mean, a lot of the outcome that we see today, a lot of the nice quantum communication system, quantum computers, quantum sensing, they are the result of decades of investment in basic research, decades of investment of students and researchers into actually make this knowledge progress and really transform this basic knowledge into something really useful. So this is a lot of work that has been done. There was one big jump or big gap that we actually jumped in the recent years, that this technology gap for all these things that are around our quantum systems, because you need to make it work and you need to make it usable for someone else. I mean, very often when I talk about quantum technology, I also make a picture with the iPhone that everybody has. I mean, if you have to know what is in your iPhone in order to make it work, then you will never be able to make it work. I mean, you have a machine which is extremely complex, which has bazillions of different components, different technologies, different tools in there. And this is what makes your iPhone so useful. And it's the same with our quantum systems. We have a nice quantum sensor, which is measuring gravity very precisely, but it is using a lot of electronics, a lot of lasers, all these things that is actually, you need to make it work all at once in order to get your quantum sensor to measure. And this was the big challenge, to make it available to people who are not quantum physicists, basically. So that's how you make a product. And the next challenge is to make it even more reliable, even smaller, cheaper, in order to extend the usability of these sensors to much more use cases, much more end users, much more markets that we can address today, for instance. There are a couple of cases where the sensors are already used. First, the fact that we, in my personal case with some collaborators, we actually started a company about 10 years ago to put on the market one of the first quantum sensors people can buy, and to put it on the market for people who were not quantum physicists, as I said before. And so geophysicists actually bought these machines. The first time they bought it because they were curious about it. And now they actually feel that they can really make a difference with it. And so they bought a machine like this and they put it on the top of a volcano in Italy, on the Etna, to look at what's happening inside the volcano. And you cannot do that otherwise, because you cannot go inside the volcano if it's active, otherwise you die. But then you can put a quantum machine on the top of it, and then it looks what's happening inside, and maybe you can predict eruptions. And so there are lots of applications in that spirit to look at things that you cannot really easily record or monitor otherwise, in order to make predictions about earthquakes, about volcanic eruptions. about water shortages and etc. For example, a lot of the internet capability comes from the fact that we can have very precise information about the time at which an information has been sent or time at which the information is received. The same way, your GPS is working extremely well because you have a very precise information about the time it takes for your iPhone to communicate to the satellite and for the satellite to come back. And this is using a quantum sensor. So everybody is today dependent on quantum technologies that are pretty advanced, even though you don't know it in a certain way. So that's what's fascinating with it.